So my talk today will be a sort of ideological talk, so no complicated calculations, but I want to sell an idea which I believe is promising. It's this idea attempts to explain phenomena of polynomial richness, polynomial patterns in finite fields, indeed rings. And let me start with something which, by the way, some portions will be known to some people. I'm sorry in advance. So here is a classical result. So Furstenberg, Sarkozy. My letters are big enough, we see well, and by the way, it goes without saying that you're welcome to interrupt and ask questions. So let P of n be a integer value polynomial, P of 0 equals 0, then for any a in n with d bar of a, which is dim sup of a intersection positive, a minus a meets the P of n for some, and indeed many, n. And this is amazing result. Each time I formulate, I try to convince the audience that it's really surprising, because A is large set, all right, but values of polynomial is a small set. Think of n squared. So it's sparse set. Y set of differences would be suddenly so large that it meets set of zero density. And this phenomenon is indeed best explained, at least to me, in Furstenberg approach, and so ergodic version.
I think that wasn't a joint paper.
What you say?
Those are, they proved it separately?
I think that it happened like that. They definitely proved separately. Methods are totally different. Sarkozy is a specialist in, sorry for saying it, logish numbers. And he did it, actually his publication came in 78, Furstenberg's publication came in 77. It was a small fragment of his big Szemer paper. Approaches are totally different, which is good, because we want many approaches. But no, it's not only not joint paper, but it's independent. I think the rumor was that, my feel is that the rumor about Sarkozy result was already there, and then Furstenberg explained it our way. And there are some, by the way, variants. Let me first all give ergodic version. So for any measure preserving system, x d mu t, for any a in B of positive measure, there exists n in n. Just each time I give a lecture, I try to stress that we're not in France, and n starts with 1. Natural numbers don't include 0. And so there exists n such that mu of a intersection t minus n square a is positive. This can be seen as, I said n square, I could say polynomial, of course, but it is with the square that was first Sarkozy result. Actually, he had 3 papers. One about square, one about maybe square minus 1, or maybe pure power. And then one about primes minus 1. And for about primes minus 1, I think you only recently understood from ergodic point of view what it is about. So here Sarkozy was ahead. But the whole explanation why polynomials in general are good, with the same more or less easy proof. And indeed, which polynomials are good? This comes because of this. So you can ask now, and why do we care that P of 0 is 0? Actually, it doesn't matter as long as P is intersective polynomial. So I will talk about this later, but intersective means that its values meet any infinite progression starting at 0. It's a divisibility problem. And that's already close to if and only if condition. So that's begin. Now, of course, Furstenberg, as we all know, had this result. So Furstenberg's Szemer ergodic Szemer theorem. And again, I will now omit quantifiers because I think we all understand what it is about. But if needed, I will just say it orally that for any measure preserving system, for any A, for any K, you have this multiple recurrence. And this, of course, is the same really as any large set, say, I should use E there, it doesn't, say E in N with D bar of E positive is reach. And I hope it's clear what this means. It has arbitrary long arithmetic progressions. This is the term which we already heard from your talk. Okay. No. If you look at this and you look at this, it takes little, effort to try to ask what about joining these two results. And that's was the starting point of Nico's system. So there is a polynomial Szemer. I will say a few words about this because the polynomial Szemer that Sasha Lehman and I proved is usually not fully quoted, namely quoted in special case, which is already of interest. But then I will explain that that's still by far not the end of the road when it comes to Szemer-like theorems. So maybe I will just write it here to save space. So our joint result with Sasha Lehman gives as a special case, that's important. I want to stress special case. Yes. So again, assume for convenience that pi of n of 0 are 0. That's for convenience. And the good question here is, I don't know, maybe I should put it up. Good. So, first of all, why is the special case? It's for single t. The general Szemer theorem that we proved was for commuting transformations, and indeed it's geometrically. So this means, by the way, this implies that any E with D bar of E positive is, let me introduce new funny notation, PP reach. And I hope it's clear what is PP in this context, polynomial progressions. Okay. Now, and again, I think this result of Furstenberg Szemer is equally surprising. So if sharp as this is surprising, the set of differences meets any specific rarefied set, Furstenberg theorem says that Poincare recurrence happens along zero density of sets. And indeed, as we all know, many of us know that due to Bourgain, we even know that pointwise ergodic theorem happens along squares. So nature likes polynomial actions. And this is still surprising because polynomial actions happen along zero density sets. Yet it works. And you get, under very mild conditions, correct limits. Okay, so the relevance for finite fields theorem of Szemer type is what we proved with Randall-McCutcheon and Lehman later. And so I would write it this way. So polynomial Szemer theorem of DL extends to modules over integral domains this is the in joint work with Sasha Lehman and Randall-McCutcheon. Maybe 2006. And this is uh, 1996. And so you see Z is just a ring. And you want multidimensional Szemer in much more general setup, which would include other domains of interest. And it turns out that it is this more general Szemer which gives the following result. So I will not formulate precisely this, but you can get the feel of it. But the corollary, so fact from BLM, and in my opinion, that's this fact that I will formulate now should be called polynomial Szemer in finite fields. So if I don't know, F, no, let me put quantifiers a little bit better. So for any polynomial that's given to you, if now if and epsilon will exist n such that if a finite field F satisfies F bigger than N, and then call this family just capital P. Then any set A in F with over F bigger than epsilon is P rich. I tried to save space. I don't know if I'm confusing people. P rich in this case would mean contains polynomial configurations coming from this family. So let me make it.
Will satisfy, are you P satisfying this P of 0 equals 0?
Yes, let us for now do that. That's a very good point. So yes.
Okay.
I write so densely Pi of 0 is 0. And that actually leads to interesting questions very soon. So is P rich, namely, I don't know, A plus P1 of N. This N is for my field, so let me write U. And Pk of U, this set is in A. Okay, so that's very similar to Szemer, and it has very strong finitistic flavor. There's some uniformity. So that's what I believe should be called Szemer theorem in finite field. There are many papers recently when people deal with specific cases, they still call it polynomial Szemer. That's really not polynomial Szemer. This is polynomial Szemer. And here, by the way, we don't make any assumptions about PIs, with the exception that they 0 at 0, and that's semi-necessary. You can extend it to intersectivity condition. Yes.
So there's a quantifier here. You allow any large enough finite field. So these polynomials are integer coefficient polynomials.
Right.
How do you?
Yes, yes, I forgot to say it, but polynomials come with integer coefficients for things to be general in
Right.
formulation, yes.
Okay.
And what is interesting here, that the field is large. So field has size p to power k. Either k is large or p is large. Let's remember that, because we will, at the end of the talk, I will hope to have time to talk about recent results with Ethan Ackelsberg, where we go to low characteristic case. That's new developments coming from philosophy that I try to sell to you, okay? But that's important, that it's the field is large, not characteristic. Okay, so we know now what is polynomial semi-radial field. And then let's go back to Sarkozy. And let me first, I will tell you what kind of, approximately what kind of result happens in finite fields, and we'll start investigating it because it's better than what you have in Z. So in finite fields, and for now, for convenience of discussion, I will take indeed the regime that characteristic is large enough. So in ZP, F with large enough E. Oh, wait, I had this part. Okay, that's different kind. That's Egyptian way of writing. You know, make a column and then you go. Okay, so there's large enough P. What happens is this, and I will come back. So let's look at this result. So of course, N for this discussion should be thought of as P itself, right? Your infinite field, your transformation T, here is X going to X plus 1, but you are in your FP, right? So it's cyclic transformation. And yet, if P is large enough, you will get this kind of statement, which for those who attended Nikos's talk is something like total ergodicity. Okay, so let's talk now about total ergodicity. In any case, if P of n would be linear, simple counting, so you're just cyclic business. So of course, P of n equal n is trivial formula and exact formula. Why for P of n being general? And indeed, for now, if you are still in this mind of 0 at 0, think of this, because that's how usually it's quoted. It's now no longer necessary, because the phenomenon of total ergodicity doesn't care about free term of your polynomial. So this is the result. You can start asking, but I repeat, n is for this framework would be just P, because you average over your P. Due to cyclicity, you don't have to take any more. But it also works, and that's important. And that's, by the way, it also works in Zn, in Z over NZ. If, now do we want to guess? If what? Surely something should be imitating this. What imitates this? Not largeness of n, but largeness of its smallest prime factor. So if L, P, F of n is large. And that's a new result which we have with Andrew Best. This part. And I think it also opens new vistas into ring theoretical polynomial semi-radial. And that's interesting, and that's actually under development. But Andrew and I have now huge paper almost completed where we do it for general rings. This is a generalization of what Sarah did in finite fields with P large. By the way, Sarah's work was great motivator. We started with some other issues. I will tell you which ones. But then Sarah's work opened some new, gave new stimuli for thinking. And I think I can now interpret your work. And we actually borrowed some of the technology. So it was good. I will mention it in a moment. So why do we care about such things? First of all, it's interesting. So what does it mean? The Charcosy now in the framework of finite, say, finite prime fields, it's not about A minus A at all. Where was A minus A? A minus A. In finite, say, prime fields at least, it's not about A minus A. Charcosy is about A plus B. B and A being totally general large sets. Okay, so the corollary would be results of this kind. A plus B contains, I don't know, P of A. That's first. So there are a few remarks to make already. If we realize that this happens, and I will start philosophizing why such things happen. So new extras are almost for free from this phenomenon is that it's about A plus B. So take any two sets of positive density in your large enough prime field, A plus B will contain n squared.
So your n is also ranging in the full finite field, right? So
n is ranging in integers which are identified with elements of this field.
So I mean, the polynomials are actually quite dense now. I mean, it's not really in a finite field. It's not really a sparse sequence like it.
That's true. That's why we should expect something better than in Z. You're totally right. So this is potentially an explanation. Indeed, let me then give one more application of this. How about this result? So fact, which is special case of the topic which is called Riemann hypothesis over finite fields. So fact is that if F finite field is large enough, and let's fix n first. For fixed n, if field, finite field F is large enough, then F is x to the n plus y to the n, x, y, and f. It's very classical result. Going back to Cauchy. And you can write here AXN plus BYN. But what is our ergodic reason for that? Whether the result with pure squares is easy, almost by pigeonhole principle. For x to the n, you have to think more. But this is corollary of this. If you take into account that field x on itself by nth powers, the nth powers in your field is a subgroup, is a multiplicative subgroup of bounded from below index. So you can take A to be exactly the subgroup of nth powers, take B minus the subgroup if you want, and then A plus B business containing P to the n is already very close to what I'm stating here. So I will leave it, it's almost an exercise now to interpret this result as corollary of this. And that's what we do actually with in explicit form with Best and Josevich in a monthly paper. So last year, I think. Terry, I see you have some.
You need what, some of 2 powers? I don't think it's true 2 powers. You need 3.
No, in finite fields, you need 2. Yeah, so n fixed, f large enough.
N, little n is fixed. I mean,
Yes, little n is fixed.
For example, if -1 is not an nth root power of n, then you can't get 0. You can't get 0.
No, these are in f, so I will get 0.
Okay, none.
non-trivial 0.
Okay.
Now it works because, and now let me start saying this to you, it works because of total ergodicity. So here is the phenomenon of total ergodicity.
And maybe define, ask somebody to define your notion of intersective Now define for us what this total ergodicity is. which-
That's I'm planning to define right now. So total ergodicity will be defined in a moment. And intersective I will define later because it's more mute in finite field setting, but it's more important for Szemer already and sharply. So X in general, X being mu t is totally ergodic if for any k in n, the k is ergodic. So irrational rotations are totally ergodic transformations. Rational rotations are not. In finite fields, everything is rational, you think. But yes, question there?
I'm looking at your definition.
So only one that
Okay.
every power of t is ergodic, that's what makes it totally ergodic. At least for z actually.
Yeah.
Now, in finite fields, everything is rational, of course. It's ergodic business, but that's exactly why we talk not about total ergodicity, but asymptotic total ergodicity. This is phenomenon of asymptotic total ergodicity, and there is one point missing, which I will now make it more clear. So, fact x e mu t is totally ergodic if, and only if, I guess, for any polynomial with integer say. Mu 1 over n mu of a t p of n b goes as n goes to infinity to mu of a. So what is behind this is again our old friend van der Korput trick, and the proof can be done spectrally if you want, by spectral theorem and the equity distribution you will get there. That's not my favorite proof because we want multiple recurrence, so we want geometric proof. Geometric proof will come from van der Korput applied to Gilbertian situation. Now, when I roll this, I hope it's clear why I called this approximate total ergodicity. I could start defining it in linear fashion, like here, but to make a shortcut, let us agree that total ergodicity is about correct behavior of polynomials. For this sake of this talk is good. Okay. So this explains already something interesting. Yes, please.
Is this approximation a limit as the characteristic goes to infinity, or is it?
Not only limit, and now I'm coming to second important for finitistic people. Finitistic people, these are people who deal with finitary situations and care about bounds. So the natural question here is, what is the speed of this difference going to zero? And then pleasant surprise. The moment you start proving this result, by the way, how you prove this? How do you verify this? Spectral method, or at least the unitary actions method. You can still use your finitistic van der Korput, but it's about unitary actions. And then for us, it was pleasant surprise that the moment you start proving it, you have a bound. So this difference between this and this is bounded by something which is small and goes to zero. And this already is visible in our paper with Josevich and Best, and in our separate paper with Best. So we have the best of all the worlds in finite fields. You still can ask what happens in more general rings, what happens in more general fields, but the phenomenon, that's something to start studying. Namely, asymptotic total ergodicity is good for polynomial recurrence. And so you get for free such things, you get for free such interesting things. Terry, I see you still think about three powers instead of two.
I withdraw my Okay.
Yeah, it's too easy now. Now let's go to multiple recurrence. So it turns out the total ergodicity extends nicely to multiple recurrence through joint ergodicity. So theorem, it was very nice that Nikos in his talk formulated this result. Let me formulate it again, because that's the I like dense packing. I could use this line, but okay, I will write here. So so this is Franzikinakis. If PIs are independent and T totally ergodic, then 1/n f on which side to write? Let me write on the side. F1 TP1 over x, F2 TP2 over x, Fk TP x goes to product of integrals. That's very nice generalization of this. Okay, so you have thank you so much. Thank you. So there are two phenomena here which together play well. This itself is what we call today joint ergodicity phenomenon, and because T was totally ergodic, you have correct limit. Okay, now I will try to give explanation why in finite fields you can expect good bounds. This, by the way, will become, you remember I said that this almost equal has good bound. And let's think of this as a starting point of some induction. Induction is much less trivial than you think. So Sarah will tell you how complicated it is. And when we deal with rings, then we have only 40 pages of pet inductions on top of Peluse Prendeville, method of lowering the degree. So it's non-trivial. However, morally, and today's philosophical talk, morally, this is the beginning of this infinite fields is bound as long as you have regime p going to infinity. So you take f e to the k, p goes to infinity. You try to prove analog of this, it works. It will give you almost equal equality here with a bound. And if you will, morally at least, this is the beginning of this induction, or very, very complicated. So I'm oversimplifying. Okay, and this is really, in this situation, will give you a result of Sarah a few years ago, right? But we have now, because of new ideology, we have some extras. What are the extras? First of all, it's about different sets. You don't have to be happy with some Szemer-like result when large set itself contains things. You take a few different sets and you spread your polynomial values in them, it will follow from here. Second thing, totally not necessary, is to assume that polynomials have 0 at 0. So we finally understand, and that should be expected, that in finite fields, some polynomial similarity should be better. And I repeat, two immediate observations already there. 0 at 0 is irrelevant now, and it should not be getting good configurations in the same set. It can be in any bunch of sets.
Is there any condition on P?
The eyes are independent.
No.
That remains.
And no condition about What's this other word that you have intersected with?
No, intersectivity is, let me try to sell what I do with Ethan, and I will come to intersectivity. I see you are interested, but
No, I'm trying to understand what we can do that's nonlinear in these kind of problems. And so
True, but in-
0 equals 0 was always.
But in finite fields, intersectivity with independent, okay, let me explain it better. If you are in finite field setting with independent polynomials, then you expect correct count. This correct statistics doesn't care about zero constant term or indeed about intersectivity. If you want to have a right generality for this result or for this result,
Yeah, that's it.
intersectivity here is obvious, that's intersecting any infinite progression, and here having joint divisibility problem. That's unavoidable, indeed necessary and sufficient, and with this intersectivity, that's actually more recent result that I had with Sasha Lehman and Emmanuel Lessine. This result, by the way, is known to us only in Z setup, so it's still huge open question how to get necessary and sufficient intersectivity type conditions and infinitary Szemer. But in finitary Szemer, either you don't have independence condition, then you should be happy with this. Okay. But because that's totally general combinatorial fact. But if you have independence, that's so much better life because you have correct limit, correct statistics, and savings coming from the fact that in finitary situation, you're getting close to zero with good estimate. And then you have all the best sides of the coin. Now I still have, how much time I have?
More than 20 minutes.
Super,
That's all.
super. Well, you're general, because last talk of the contract. So in any case, then I want to tell you what we very recently did with Ethan. So this workshop was very stimulating. We worked hard to finish our result just before my talk, and good the talk is on Friday, not on Monday, because we uploaded two preprint just in the last 2 days. And so here's a new very interesting setup, which we now want to complement this result of Sarah and more general result, which I will not have time to explain, but with Andrew Best, we know to do such things for rings. The only condition which replaces this is this LPF business. So we have really quite uniformly correct result under independence assumption for rings whose characteristic has property that the lowest prime divisor goes to. So this seems to be satisfactory, but this is now a new question. What about going to infinity fk when p fixed k goes? Totally different regime. And
You have two Ks, that's confusing. K is the number of your polynomial.
M. No, but
Okay, one more thing there.
this guy is okay.
F sub m, I think you want to write
The function.
the function.
Yeah. Okay. That's interesting. That's totally new challenge. Now, it corresponds to what they call finite characteristic. So arguably, this was asymptotically infinite characteristic, and now we want finite characteristic. P is fixed. And now the total new game starts, which is very interesting, both algebraically and analytically. Namely, you have to rethink everything and make analogies. Luckily, Sasha Lehman and I, some time ago, had a paper on uniform distribution and finite characteristic, and it turned out to be very useful. So in finite characteristic, what corresponds to Z is this ring. Okay, and that's, I think, not new not new discovery. So polynomials over FP, this is our new Z. And in this new situation, it's people who do number theory in function fields know it much better than me and more generally than me. But if you have Z, you start asking what is Q. These are rational functions. What is R? It's the Laurent series. What is torus? It's corresponding factor space. So you have all the important items convenient for dealing with uniform distribution and similar to what Hermann Weyl did for his famous polynomial theorem about uniform distribution. And Sasha Lehman and I worked on that. And then there is immediate observation that there are two cases. If all polynomials have degree smaller than characteristic, then up to new method of averaging, because you have to go through Felder sequences, which you have to invent in this set. It's easy. You take polynomials of higher and higher degrees. You have uniform distribution, and this was observed already by some Dutch people in the 50s. These Dutch people came up with counterexample for polynomial of degree higher than or equal or higher than characteristic, and declared morally that there is nothing else to study there and stopped doing it. And so Sasha and I attempted to understand what happens if you have polynomials of higher characteristic. And now together with Ethan, we are trying to do and succeeded to understand what happens with higher, let's call it low characteristic case, higher degree case. That's what we deal with. And then the very first thing, very interesting on its own, is that the Weyl theorem, the famous Weyl uniform distribution theorem, is now more subtle in finite characteristic case. If polynomials, as I said, are of degrees lower than characteristic, then it's the same game. But if polynomials are of higher degree, for example, n to power p. This is n, by the way, comes from my field theoretical notation, right? So polynomial n from f t, okay? So I take this polynomial and I want times alpha. You should ask me what is irrational alpha, but I think it's clear what it is, right? You take r minus q. You have new r, new q, you take r minus q. You want this times alpha to be uniformly distributed, is it? Not for every irrational one. So there is a interesting new life. And why? Partly because this is a polynomial, all right, but it's actually linear in a way, and it's additive. And there are new polynomials, which if you want to treat by van der Korput and everything, you have now to invoke not only the degree, that's maybe minor now, you have to invoke, how do we call it, derivational degree, right? It's a question how many derivatives will kill it. And it works, at least the results are more complicated. And then there are interesting cases when you have still, we call them irrational equidistribution good polynomials, but it is, and our discovery is that the irrational equidistribution good polynomials, that's what replaces this condition. So when you are in large P case, that's the correct condition. But if you are in small p case, you have to be more careful with the notion of independence in order to get at least the correct ideology, correct results of this kind, at least finitistically. And the correct assumption is that these polynomials have to be good for irrational equidistribution. So take my word that this is natural, and to understand better, if your polynomials, you see the trouble is when you have some polynomial with powers which are multiples of p. So if you don't have the powers divisible by p, we call them, I don't know why, Sasha and I call them separable. For separable polynomials, linear independence and being good for irrational equidistribution coincide. But in general, that's the condition. And now I can briefly tell you what are our results. They're actually the same in a way that we know from high characteristic, the same Sarkozy type result. You have to formulate it in new in new algebraic framework, but the same Sarkozy with A, B, and savings, and the same Sarah-like result with A1, A2, other sets, and savings. And this is the contained in the very last two preprint that we had in the last 2 days. And now, how much time we have?
Well, 10 minutes, let's say.
So
Yeah.
there is the work of Ratner, Molchev about unipotent dynamics in this setting, which maybe who did it? Mohammadi? Who's developed Ratner? Which is much more complicated to develop the Ratner measure rigidity in the setting of unipotent in this function field setting. I believe they have some breakthroughs. You familiar with
So
it?
I think what you talk about still will be infinitary life. Here we are in finite setup. We use this field, this ring only as a source instead of Z. But now that you asked your question, I wanted to stress the phenomenon of asymptotic total ergodicity, because I find it very, very interesting and parallel to notion of quasi-random groups. Let me say a few words about this because it's very suggestive. So what is quasi-random group? It's actually, by definition, it's not a group which is quasi-random, it's sequence of groups which are quasi-random. But which groups are quasi-random? This is definition of Gowers. Groups are quasi-random in my ergodic person language if their actions on themselves are asymptotically weakly mixing. Now, in terminology of finitistic people who care about quasi-random groups, definition is different, but now some of you will see why it is connected. Suppose you have sequence of groups, maybe, and examples would be PSL of groups which are quasi-random would be, for example, AN, the alternating group, PSL of 2F. There are two regimes here. F can go, the size of F goes to infinity either through P or through K. In both cases, these are quasi-random sequences. And what is the definition in terms of spectral theory, if you will? Sequence of groups is quasi-random if the smallest unitary non-trivial representation of this group goes to infinity, the size goes to infinity. And we all know this. We know, for example, sequences of simple groups have this property. It's very poignant property, but ergodically, it's just asymptotic weak mixing. And now what we suddenly have with Andrew West and Ethan Ackelsberg, we have asymptotic total ergodicity. This is something which should be understood maybe more deeply. We apply it as a heuristic so well. So the problem in both setups is hard to solve. What is here we know what could be, it's up to you, what is limiting case of such things? Maybe infinite alternating group, that's easy. What is limiting case here? Suppose it's FP. So here is a sequence of groups. It's asymptotically weakly mixing. So Terry and I had a paper, hard to read paper, where we used non-standard analysis to argue that if you get in the limiting object something good, and what do you get in limiting object? Weak mixing. Then you can go back and get results. Then of course came Tim Austin and made it simpler and eliminated the need in even thinking about limiting object. But I think it's still interesting. Limiting object here and limiting object here are similar questions. But phenomena are also similar, right? So here you have asymptotic weak mixing, here you have asymptotic total ergodicity. Now, total ergodicity, again, ergodically has different setups in Z, and not all of them extend nicely to more general situation. In Z, if you want to think spectrally, total ergodicity is small or no. Total ergodicity, no rational spectrum, no functions which have rational eigenvalues, no finite orbits. This is one approach, and there are additional interesting things. And so that's why the notion is interesting and promising. And that's what is our next goal with Ethan. We are not fully done. So remember, I told you that results was when P goes to infinity, which we have with Andrew Best, they apply also to rings, not necessarily to fields. Now, there is one natural analog of this ring in low characteristic situation, and there I think we understand things at least for single recurrence. But what is not clear to me, maybe algebraic people can help me, the rings based on low characteristic, how multiple they are, how interesting they are, how natural they are. That's less clear, but analog of this definitely is there, definitely is natural, and that's where we try to get maximum knowledge. I think I should stop now, and thank you for attention.
Much, Vitaly. Do we have questions?
Yes.
John.
Just maybe, if I take the affine group of a finite field, is that a random group? Is this family?
No. No, because it has additive part. It is a mixed case. This is a mixed case. You see, those correspond, by the way, again, historically. So it was paper by von Neumann and Wigner when they introduced minimally almost periodic groups. Minimal almost periodicity is really about asymptotic weak mixing. And they give you different examples, and the solvable business is somehow in between.
But they do have some interesting properties, these affine. If you look at the proof of Castan's property T, it uses this affine part with a kind of twist in it, which does have then an expander property, which is what he's talking about. So expanders were constructed this way by Gauber, for example. I can show you. So yeah, it's certainly not got a spectral.
The random groups have to be perfect. They can't have any abelian quotient.
So they're representations which are bad, but they are representations which are good, which are the ones that are certain growing ones, and those are used there.
Yeah, these are mysterious things. You see, we like so much and so naturally work with manifolds, but it seems that solve manifolds is totally crazy thing. Yeah.
Okay.
So can I ask about this independence condition you're imposing on the PIs
Yes.
in your result? That is the analog of Franz-Bianchi's curl here. How does that look?
In the local characteristic? Or
No,
in
just
this case, it's independence. That's what you assume in order to get correct statistics.
yeah. So the independence is polynomials with integer coefficients. It's not formulated in terms of the field.
No.
Right.
Integer coefficients you prefer in order to run through different fields and not to worry.
Right.
There are interesting aspects of considering other coefficients, but we are not there, and maybe it's natural enough to have integer coefficients.
Mhm.
And then if the field is large enough, then coefficients will not cause you local abstraction.
Is that independence condition formulated there as integer polynomials known to be the right sort of, or the optimal assumption there for this type of?
For correct statistics, I
Yeah.
believe, yeah. So that's exactly whatever you have with infinitary situation, you would have analog of it infinitary. So you want correct statistics and savings independent. That's why it was surprising that in in low characteristic, and they had to amplify the condition of independence.
Thanks.
More questions? Well, okay, so let's thank Vitaly.